Hello, everyone. So now we have a good general idea of electrochemical cells. So we're going to go ahead and focus a little bit more on what the key piece of information that they tell me about is, namely electrochemical potentials. So if I have essentially an electrochemical cell set up in, again, two half cells, I'm letting electrons move from the anode to the cathode. This is going to give me an energy measured in volts. So now what I'm very curious is, what does this voltage passing through the cell really tell me about the system? So we've already been able to ascertain that a potential is going to be related to the maximum work that's essentially stored in a system. So if I have the potential, this is going to be related to the negative of the maximum amount of work. But one of the other important features here is that the type of work we're talking about in an electrochemical cell. Because in an electrochemical cell, moving electrons is definitely considered non-PV work, which means that my potential is going to be related to the negative of the free energy of the reaction that I'm essentially, of the redox reaction that I'm essentially measuring in these two half cells. And this is essentially the major idea behind electrochemistry. The measured potential is equal to the negative of the Gibbs free reaction. But we have to watch out for one major issue, and that mostly comes down to units. Because our potential is going to be measured in volts, whereas our Gibbs free reaction is typically measured in joules or kilojoules per mole of reaction. Well, it turns out that these two units don't match up nearly as nicely as we'd like. So I need a way to try and equate these two terms. Well, a good place to start is going to be on the definition of a volt. So a volt is going to be the joules of energy that we essentially gain per coulomb of charge that we allow to travel through the system. So again, the more charge in the system, the less joule per charge. So now I've got to watch out for more or less some pesky unit conversion that's going to be trying to turn these joules of energy to essentially moles of reaction, this coulomb of charge to moles of reaction, which will allow my units to line up. So first of all, we do maintain this idea that a positive potential and a negative free energy both indicate work being performed, indicate a favorable reaction. Because in potential terms, this is the volts that I am gaining by letting the reaction proceed. And in Gibbs free energy, negative values indicate a decrease in the free energy or a release of energy. So again, the first thing we notice is this negative sign issue. Second, we can make use of Faraday's constant, which is essentially a conversion in between coulombs and moles of electrons. So essentially, 1 mole of electron has 96,500 coulombs of charge. And then what we can do is say, well, if this is coulombs, well, a volt is joules per coulomb, so this means that Faraday's constant also has units of joules per volt per mole of electron. And this is really going to help a lot of our units come together, because now I have a potential in volts times Faraday's constant, which then just gives me joules per mole of electron. So the only thing I have to cancel out is going to be this moles of electron. And we do this through our N factor. So here, one of the things I really want to emphasize is that N isn't just the number of electrons being transferred. It's the number of electrons being transferred per mole of reaction. Because what this suddenly does is it takes my potential, which is more or less giving me the joule, when I pair it with Faraday's, is giving me the joules per mole of reaction, and it turns it to joules per mole, or joules per Faraday times potential gives me joules per mole of electrons, and by multiplying it by more or less our stoichiometric coefficient of electrons gives me joules per mole of reaction, which is, again, that Gibbs free energy that I'm really after. So we can take this idea and apply it to a real chemical system. And again, if I'm looking at my lead acid battery, it has a standard state potential of 2.05 volts. So I can turn this into the free energy of this reaction. Well, the first thing we're going to want to know is the number of electrons being transferred, which last time we showed that by balancing our two half reactions, that we have uh, 2 moles of electrons that are essentially transferred from the lead to the lead oxide as they both form lead sulfate. So using this, I can determine the free energy of reaction using the moles of electrons per mole of reaction, Faraday's constant, and the potential of the system. When I put this all together, we have a free energy of reaction of a little bit under 400 kilojoules per mole. So again, this is demonstrating a very exergonic reaction. This is a very, very favorable reaction, which is one of the reasons why it's used so widely as a battery, because it has a lot of excess energy that can be captured to drive other chemical reactions or just set off your spark plug in your car. But one of the things that we do need to keep an eye out for is the fact that this is going to be the standard state free energy and the standard state potential. So it does turn out that the energy available from this reaction is going to change with the concentration of the system. And this is something that we should acknowledge. So we know how free energy of reactions change with concentration. And let's try and use what we know to figure out how the potential changes with the free energy of reaction. So I can go ahead and start with my classic unit conversion in between potential and free energy, and then pair this with our concentration dependence of the Gibbs free energy. Where again, just as a reminder, because it's been a bit since free energy, the free energy of reaction is equal to the standard state free energy of reaction plus RT, natural log of the reaction quotient. So in a more general term, what we can do is substitute in our potential expression for both the Gibbs free energy of reaction and the standard state conditions, which is a little bit bulky until we start noticing that both our potential term and our standard state potential term both have prefactors of negative NF. So I can divide the whole expression by negative NF, and I get the potential equals the standard state potential minus RT over NF, natural log of the reaction quotient. So this is more famously known as the Nernst equation, which is really just our Gibbs free energy equation, just rewritten in different units. So this is actually a little bit more familiar than we might expect. But again, we do have to acknowledge that a reaction quotient is going to be more focused in on moles of reaction, which is really what the R is telling me here. So I do need to allow for unit conversion to go from moles of reaction to moles of electrons. And this is going to drive a lot of the differences in between how we use potential and how we use free energy. But we can also use some of the same tricks that we've used for our free energy equations. Most notably, we can apply this equation for equilibrium conditions. So under equilibrium conditions, E equals 0, because the potential at an equilibrium reaction is going to be the same as the Gibbs free energy at equilibrium. That's 0. And Q becomes K. So it turns out that if you've got a redox reaction and you're able to measure its potential, you can actually fairly quickly determine the equilibrium constant simply by measuring the standard state potential and having a balanced reaction. So this is incredibly powerful. However, we can also try and figure out how my actual potential is going to change as a function of concentration. And this is a good exercise to illustrate the sheer variability in the chemical potentials of a system. So let's go ahead and go back to our good old friend, the lead acid battery. And I want to figure out how the potential of this battery changes with concentration. So we can go ahead and start with our Nernst equation. And then we're going to need to start substituting in the key terms, most notably the reaction quotient, which again is products over reactants. But here we start to get fairly lucky because lead, lead sulfate is a solid, water is a liquid, lead oxide is a solid, and lead is a solid. So none of these will show up in the reaction quotient because they all have activities of 1. This just leaves me 1 over the activity of sulfuric acid squared, which in truth, we're often going to is a strong electrolyte, so we're often going to split it up into its base components of sulfate and protons. Because again, when I'm dealing with a strong electrolyte, we're going to treat the individual ionic components. And we'll also use this to illustrate some fairly neat points. First of all, since I have the multiplication of these two, I can go ahead and separate them into 2 separate expressions. And specifically, for reasons we'll see later, it's very nice if we pull our activity of our proton up into the denominator, which is the same as taking the negative of the log. But since I have a negative log to begin with, we're going to generate this one as a positive log. So thus, we have a negative natural log of 1 over the activity of the sulfate squared, whereas a positive natural log of the activity of the proton to the 4th. Then we're going to play a couple other cute mathematical tricks. Because the activity of the the activity of the sulfate is squared, I can go ahead and pull that square out into the front of the natural log. So now I have an expression of just natural log of 1 over the activity of sulfate, which is a much more friendly expression to deal with. And we can do a similar trick with our activity of the proton by pulling out the exponent into the prefactor. But we're going to pull one other cute little trick. One way that you can change the base of a log is to essentially pull log of the original base system. So we can use log of E times log of the activity to give us the same thing as natural log of the activity. So when we do this, it turns out that log of E, and again, this should be log, not natural log, is 2.303. So I get a hard number here. And then I can go ahead and put in all of the rest of my numbers. Now, under standard state conditions, it is worth acknowledging that RT over F is equivalent to 25.7 millivolts. So I'll go ahead and substitute that in for RT over F. This just leaves me with the 2 from my activity exponent and the 2 from the number of electrons. And then we again play similar tricks with our activity of our proton concentration. 4 for the exponent, 2 for the number of electrons being transferred. Now we can play one last cute trick. So I can go ahead and cancel out the 2's in front of the activity of the sulfate. So now I have an expression with the potential is equal to the standard state potential minus 25.7 millivolts times the natural log of the activity of the sulfate, 1 over the activity of the sulfate. Now, if you so desired, you could treat this as plus 25.7 millivolts times natural log of the activity of the sulfate, again, in the numerator. But one of the big points that I really want to illustrate is this last cute expression, because it turns out we know what negative log of the activity of a proton is. This is the very definition of pH. So I can replace any log of the activity of a proton with the pH of the system. Thus, we see another sign change, and then I collapse the rest of these numbers into 113.8 millivolts. So sometimes when you're dealing with these kind of more messy descriptions of activities and concentrations of a system, one of the things you can do is figure out how you can go ahead and try and rearrange it into a little bit more kind of concise forms. So one classic trick is to go ahead and play around with your exponents and your various variables by collapsing them down into simple numbers and getting rid of any exponents inside the natural log. Another trick you can do is anytime you see activity of a proton, remember, that's just going to be pH. So we can change our basis with, again, log of E, as well as playing some other fun, cute tricks. So this gives us a way to try and evaluate how the potential of a system is going to be pH dependent. And again, one of the things that you'll make note of here is that I'm going to have a higher potential with a higher sulfate loading. But again, as I increase the pH of the system, I decrease the effectiveness of a battery. So thus, this is one of the reasons why lead sulfate batteries tend to run at very high sulfuric acid concentrations. Because A, it keeps my pH very low, and B, it keeps my sulfate concentration very high. Now, we should be able to anticipate some of these by, again, just going back to our simple chemical equation and noting that sulfuric acid is a reactant, and Le Chatelier's would predict a more favorable reaction with higher loadings of the reactants. So again, a lot of this is just another way to look at Le Chatelier's and some of our chemical equilibrium principles. So next time, we're going to take some of these ideas of chemical equilibrium and potential and apply them to some of our good old thermodynamic functions. Until then, take care.